Longitudinal waves, Physical Sciences, grade 10. Before we talk about longitudinal waves, we first need to revise our understanding of a transverse pulse. The demonstration on your screen shows a transverse pulse. A pulse is a single disturbance moving through a medium, like from one side of the medium to the other. Just look at that pulse from left to right. Look at it. You see it, right? This is the pulse. It is a disturbance in a medium that is otherwise at rest. The medium is made up of small particles represented by the black circles. The pulse is in one direction, left to right, that is horizontally, and the particles of the medium are displaced in a different direction, up and down, that is vertically. But what do I mean when I say that the particles of the medium are displaced up and down? I mean that their position changes from equilibrium to a highest point they can reach, then back to equilibrium as the pulse sweeps through them. Okay, let's say the green line represents equilibrium position. Then the blue line represents the highest position the particle of the medium will reach in the vertical axis. I want us to focus on the first particle over here, the one that I've circled in red. As the pulse sweeps through it, the particle looks like it jumps from equilibrium to its highest point, then back to equilibrium. The particle goes up, then down as the pulse goes through it. This means that the particle's change in position is in the up and down direction, or it is in the vertical direction. Now, the vertical and the horizontal directions are said to be perpendicular to each other. This type of pulse, where the direction of motion of the pulse relative to the direction of displacement of the particles is perpendicular, is referred to as a transverse pulse. The same is true for a transverse wave. Now that we understand the movement of a transverse pulse through a medium and how the particles of that medium are displaced, we can talk about a longitudinal pulse and later on a longitudinal wave. The demonstration on your screen shows a longitudinal pulse. A pulse, as I've mentioned, is a single disturbance moving through a medium. The pulse sweeps through this medium from left to right horizontally, right? The medium is made up of small particles represented by these black circles. As the pulse sweeps through the medium from left to right, the particles of the medium are displaced in the same direction as the pulse, horizontally. The two directions are parallel. When I say the particles of the medium are displaced in the same direction as the pulse, I mean their change in position, their position changes from equilibrium to a maximum point they can reach, then back to equilibrium. Let me show you how. Let's say the green line represents equilibrium. Let's focus on this one particle here. The particle appears to be pushed, let's look at it, to be pushed to the left as the pulse sweeps through it. The particle then appears to push the next particle in the second column to the left and then comes back to equilibrium. Let's have a look. It's pushed to the left, then comes back to equilibrium, right? So this means the particle leaves equilibrium to a maximum distance to the right, then back to equilibrium. What does this mean? This means that the particle's change in position, or what we call displacement, is also horizontal. This type of pulse is called a longitudinal pulse because the direction of motion of the pulse relative to the direction of displacement of the particle are parallel. This means that there's a 0-degree angle between the two directions. Hence, for a longitudinal pulse, the direction of motion of the pulse is parallel to the direction of the displacement of the particles of the medium. The same is true for longitudinal waves. Let me explain this idea of parallel and perpendicular a bit better. Here is a protractor. For a longitudinal wave or pulse, the direction of motion of the wave is from left to right, or sometimes it can be from right to left, as long as it is in the horizontal direction, right? So in this case, it is from left to right. The direction in which the particles of the medium are displaced is also from left to right. These two directions are said to be parallel to each other because there's a 0-degree angle between them. That is, they point in the same direction. However, for a transverse wave or pulse, the situation is slightly different. The direction of motion is from left to right, and the particles change position or are displaced in the vertical up or down direction. There's a 90-degree angle between the two directions, and hence we say that they are perpendicular. Now that we understand longitudinal pulses better, we can turn our attention to longitudinal waves. At the end of this lesson, you will be able to define a longitudinal wave, draw a diagram to represent a longitudinal wave in a spring, showing the direction of motion of the wave relative to the direction in which the particles move. You will also be able to define a compression or a rarefaction and define the wavelength and amplitude of a longitudinal wave. In physical sciences, a slinky is more than just a toy. A slinky for us is a very useful tool to help us understand longitudinal waves. By moving the slinky back and forth, longitudinal waves can be demonstrated. As the orange slinky is moved back and forth, we see that there are regions on the slinky where the spirals are closer together and regions where the spirals are slightly far apart. This is like with a longitudinal waves, the diagram of which we draw like this. A longitudinal wave is a wave where the direction of motion of the parallel of the wave is parallel to the direction in which the particles of the medium are displaced. This means that if the direction of motion of the wave is horizontal, the direction of displacement of the particles of the medium will also be horizontal. Therefore, a longitudinal wave is a wave where the particles of the medium move parallel to the direction of propagation or movement of the wave. Or another way we can define a longitudinal wave is that it is a wave in which the particles of the medium vibrate parallel to the direction of motion of the wave. As you can see on the diagram of these longitudinal waves, there are regions where the spirals are closer together, like here, 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 and here. This means at those regions, the particles of the medium are closer together. They are pressing and pushing against each other hard, meaning that there is a lot of pressure at that region. We say that it is a high pressure area. This region where the pressure is high is called a compression of a longitudinal waves. However, there are also regions on this diagram where the pressure is low. The spiral, meaning that the spirals are far apart from each other, such as here, here, and here. This region of a longitudinal wave is called a rarefaction. This is the area of low pressure. Longitudinal, this means that at these regions, the particles at these regions are far away from each other. Longitudinal waves are referred to as pressure waves because they have regions of high pressure where the particles are closer together, referred to as compressions, and regions of low pressure where the particles are far apart from each other, referred to as rarefactions. Therefore, we can define a compression as a region in a longitudinal wave where the particles are closest together, or a region of high pressure in a longitudinal wave, right? A rarefaction can be defined as a region in a longitudinal wave where the particles are further apart from each other, or a region of low pressure in a longitudinal wave. Let's say we had points A, B, C, D, E, F, G, H on these longitudinal waves. These points, if you look carefully, are located at the start or end of a compression or rarefaction. The distance from A to C and C to E and then E to G are equal and are a wavelength apart. This means that the distance from A to C represents the wavelength of a longitudinal wave lambda. The symbol for the wavelength is the Greek letter lambda. Also, the distance from C to E represents the wavelength of a longitudinal wave lambda. And the distance from E to G represents the wavelength of a longitudinal wave lambda. These points, A to C, C to E, and E to G, are said to be in phase because they are a wavelength apart. They are separated by a complete wavelength. Similarly, the distance from B to D, D to F, and F to H are equal and are a wavelength apart. This means that the distance from B to D represents the wavelength of a longitudinal wave lambda. Also, the distance from D to F represents the wavelength of a longitudinal wave lambda. And the distance from F to H represents the wavelength of a longitudinal wave lambda. These points, B to D, D to F, and F to H, are said to be in phase because they are a wavelength apart. But what do I mean when I say that these points are in phase? I want you to look at the pattern of this longitudinal wave from points A to C, as well as points C to E, then points E to G. What do you observe which is similar between these three regions? So, if you look at this region of the wave over here, from points A to C, and this one over here, C to E, then this one over here, E to G. What are the things that you can say are the same between these three regions? By looking at these three regions, I would say that they look the same. It is as if one region is repeating itself over and over again. Do you agree with me? Remember, we said that the distance from A to C, or the distance from C to E, or the distance from E to G is a wavelength, right? This means that after each wavelength lambda, the wave repeats itself over and over and over again. We can clearly see that 2 points are in phase if they are separated by a complete wavelength or a multiple of wavelengths. What do I mean? Or complete multiple of wavelengths. But what do I mean by that? Points A and C are in phase because they are separated by one wavelength. Points C and E are in phase because they are separated by one complete wavelength. Points E and G are in phase because they are separated by one complete wavelength. But for points to be in phase, they do not need to only be separated by one complete wavelength. They are also in phase if they are separated by two complete wavelengths. For example, from point A to E, there is two complete wavelengths. That is lambda plus lambda equals to 2 lambdas, two complete wavelengths. There is 3 complete wavelengths between points A to G. That is, there is lambda plus lambda plus lambda, which is equals to 3 lambdas. That is 3 complete wavelengths. This means we can define the wavelength of a longitudinal wave as the distance between 2 points or 2 adjacent points or 2 successive points which we say are in phase. We have described the wavelength of a longitudinal wave. What is then the amplitude of a longitudinal wave? Remember in the beginning when we were talking about a longitudinal pulse, we said that the particle leaves equilibrium towards the right, then back to equilibrium after the pulse sweeps through it. This means that the particle leaves equilibrium, then back to equilibrium after the pulse has passed through. The change in position from equilibrium to the maximum distance to the right is referred to as the amplitude. Therefore, the amplitude of a longitudinal wave is the maximum displacement of a particle from its equilibrium position. Shoo! We have finally come to the end, at least for now. In this lesson, we have learned about longitudinal waves and that they are made of regions referred to as compressions as well as rarefactions. We have also seen how to determine the wavelength of a longitudinal wave. And lastly, we learned the definition of the amplitude of a longitudinal wave. The next video, we will look at a few examples on how to calculate or determine the frequency, the period, and the speed of a longitudinal wave.